Hey everyone, welcome back, and today let's solve Leetcode problem 1975 titled Maximum Matrix Sum. So we're given an n by n integer matrix and we can do the following operation any number of times. We can choose any two adjacent elements of matrix and multiply each of them by -1, or essentially just make them negative if they're positive or positive if they're negative. And two elements are considered adjacent if and only if they share a border, or in other words, if they're four directionally adjacent. Our goal is to maximize the summation of all the matrix's elements, and we need to return the maximum sum of the matrix's elements using the operation mentioned above. So in example 1, we have a 2 by 2 area of 4 input matrix of the cells 1, -1, -1, and 1 for our corresponding rows. And if we choose these two highlighted cells in this image and multiply each of them by -1, or basically make them positive from negative, then you can see that we'd end up with a final result of 1, 1, 1, 1. And that is the maximum sum we can make because all of our cells are positive, right? Positive values are good, and we want to minimize the number of negative values that we have because they take away from our total maximum sum. And in this case, since all of our values are positive, that's the best we can do, and we simply output 4. In example 2, and they also give us the process of how do we get there. We can multiply the first two elements in the first row by -1, and then multiply these two by -1. So first we multiply these guys, then we multiply these guys, and then we end up with 1, 1, 1, 1. Okay, so in example 2, we have our input matrix to be the following. It's a 3 by 3 in this case, and we output 16. Why? Because we can multiply the last two elements in the second row of our matrix by -1. Then they become 2 and 3. And there's no other optimal way we can do this, and so we would output 16 as our maximum result. And a good observation you can make in this example is that why are we changing -2 and 3? Why not -2 and 1? Well, if we change -2 and 1, we get 2 and 1. That's good. We're still increasing our sum. But if we change -2 and -3, we get 2 and 3. That has a sum that contributes to our total sum a lot more than 2 and 1. In other words, we're taking the largest absolute value of the possible cells that we can make positive or multiply by -1 to maximize our sum, right? And that leads us to our next observation. Now, in example 2, we saw that in this example we had two negative cells, or in other words, we had an even number of negative cells, or cells with negative values. And when that's the case, we can, through some process, eventually make all of the cells in that matrix positive because we have an even number of negative cells, right? And we swap two at a time, so we can eventually make them all positive in some process or some way by reaching all of the cells. However, when we have an odd number of cells, like we saw in example 2, that have a negative value, then we can flip all of them except for 1 to actually make sure that we have at least one or an odd number of elements that have a negative value, right? Because again, we don't want cells with negative values. They hurt or basically take away from our total maximum possible sum. And to actually make sure that we maximize our sum, when we have an odd element, we simply want to take all of the elements and take its absolute value, except for the element or cell with a negative value that has the smallest absolute value. Or to better put this in words, in this example, we saw that all the cells with negative values, by the way, there was an odd number, there's 3 of them, were -1, -2, -3. We changed -2 and -3, the adjacent cells, to be positive. Why? Because that would give us, because they had the largest absolute value out of all the other ones, right? -1 had the smallest. And so even if we kept this -1, which we did because we have to have at least an odd number of negative cells at the end, that doesn't hurt our maximized sum as much as it would if we took -2 and -1, because then we'd have a -3 that we're taking away, which is a lot worse, which takes a lot more from our maximized possible sum. Okay, so with that out of the way, I will give you guys a few seconds. I'm going to just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so if you haven't yet, try to just use the observations that I show you guys in the first part of this video. And now I'm going to actually kind of put this into a formal solution, kind of a high-level rundown of our solution that we can actually use to solve this problem cleverly. Well, first of all, we simply need to calculate the sum of all of the absolute values of all of our elements in our matrix. And what does that do? It makes sure that any negative number or negative cell's absolute value will still contribute positively to our sum in the case that we make it positive. But we also have to track the smallest absolute value in the matrix, like we saw in example 2, right? And that's going to help us adjust our sum if and only if we have an odd number of negative values, because it can be the cell that we don't make positive, right? The smallest absolute value, so we don't hurt our sum as much as we possibly can, right? And as we're actually taking the absolute value and adding it to our running total sum in our input matrix, we also want to count how many negative values are in our matrix as well, right? And if the count is odd, then we have to flip one negative, or rather flipping one negative to a positive is not going to balance the matrix, right? So we have to adjust the sum by subtracting twice of the smallest absolute value, and you'll see how that is in the code. I will explain it a little bit more. Okay, so now with that out of the way, let's go ahead and dive straight into the code here. So I'm going to initialize my total sum to help me actually calculate the total sum of all the different absolute values of all the elements in our matrix. So it's going to be initialized to 0. Now I'm going to have my minimum absolute value, right? Basically the minimum absolute value of any cells that we find. That's negative, so that can be the cell that we don't switch when we have an odd occurrence of negative cells. And it's going to be initialized to the float of infinity. Why? Because we want to actually minimize it as we go. And this is going to kind of be our base case here. Now, right? And again, it's basically going to store the smallest absolute value among all the cells that we find in our matrix. And if we, again, start with the float of infinity, right, basically the largest number known to mankind, it's going to make sure that any actual number that we see is going to be smaller and help minimize this variable. And then finally, we're going to have a negative count, which is pretty self-explanatory here. It's simply going to keep track of how many negative numbers we actually find in our matrix. Now let's actually start iterating over our matrix. So for every row in our grid, we want to then loop through all the values in this grid. So for every row in the grid, and for every number or cell in that current row, right? One is the outer loop for looping through all the different rows, and the inner loop is to loop through every single element in that current row, right? Which is going to help us process each element in their matrix one by one for each row. And for every single number in this row, we want to add to the total sum of our matrix of all the different elements and their absolute values, the absolute value of the number, right? Because even if it's negative, we're allowed to multiply it by -1 however many times we want, and we'll handle the case when we have an odd number of positive, or rather of negative cells when we actually cross that bridge. Okay, now that we've actually made sure that all the numbers contribute positively, or the absolute value to the total sum, now we can take the minimum of the current minimum absolute value and the absolute value of the current number. So minimum absolute value is going to be the minimum of itself, because again, we don't want to make it smaller. We want the minimum cell, or we want the cell with the minimum absolute value, so that can be the one that we exclude in our sum that we actually make to positive, and of course, the absolute value of the current value. Right, this is the one that we're currently adding to our current sum, but if it's smaller than the minimum absolute value for any cell that we've recorded so far, we want to update our minimum absolute value to be the minimum of that value, right, which is again going to keep track of the smallest absolute value in the matrix, right, and that's going to be crossed if we actually have an odd number of negative cells. If that's not the case, then we can flip all of them to actually be positive, and so we don't even have to worry about this variable. Okay, now that we've done that, now we have to actually check if the current cell that we're looking at, the current number or cell in our current row in this iteration, if it's actually negative or not. So if the current number or cell value, if that's less than 0, in other words, if it's negative, we want to increment the number of negative cells we've seen by 1. So negative count plus equals 1, right? Pretty self-explanatory. This is going to keep track of the number of negative values or cells that we actually encounter as we iterate over our matrix. Now we have to actually check if we have an odd or even number of negative values. So if the negative count, modded by 2, where's the percentage modded by 2, if that's equal to 1, right? So if there actually is a remainder, then we know that it's odd. And if the number of negative cells in our matrix, if it's odd, then there are going to be leftover negative signs that we can't cancel out, right? And if that's the case, that's going to impact our ability to maximize the sum. It's going to take away from our sum. But we want to take away the smallest value, right, or the smallest absolute value of any of the cells, which is why we use this minimum absolute value variable. In this case, once we actually process all the elements, the minimum absolute value in example 2 would be set to -1, right, because that would be the cell that we can exclude to take away the least of our maximum sum, to make it most optimal to maximize our sum of all the different elements and their absolute values once making all the negative cells positive. So if we have an odd number of negative cells, we want to then subtract from our total sum of our matrix. So minus equals 2, like we talked about before, times the minimum absolute value cell, right? But why are we doing 2 times the minimum absolute value cell? Well, again, if the number of cells that we actually have that are negative are actually odd, then we have to adjust our sum, right? Our total sum of all of the sum of all of the elements in our matrix. And we can do this, or we have to do this by subtracting twice the smallest of the absolute value, right? But why is that? Because that actually helps us account for the fact that we have to flip the sign of the smallest number to make the negative count even. And once we've actually taken care of that smallest value, if we have a negative number of negative cells, we simply have to return the final value of our total sum of the matrix, right, which is going to represent the maximum possible sum of our matrix after these necessary adjustments. And unless I made any syntax errors here, this should be accepted, and this should be a valid solution. And as you can see, this is actually just about as efficient as you can get. So for a quick high-level rundown and reiteration of how this code actually works, well, we're simply just calculating the maximum sum of our matrix by simply first adding or summing all of the absolute values in our elements and incrementing that to our total sum. And also, we're adjusting for any odd number of negative values using our minimum absolute value, which is going to keep track of the smallest cell with the smallest absolute value. And that makes sure that we maximize the matrix sum while also complying with the rules that we can only swap 2 cells at a time, right? And basically making them positive or negative if they're positive already. Right, so for the time complexity of this solution, this is going to be a big O of m times n solution. Why? Because we're iterating over all the elements in our matrix exactly once with these nested loops. And the space complexity or the memory complexity is going to be big O of 1. Why? Because we're actually using a constant amount of extra space. It's not actually growing directly with our input because we're not also using any extra data structures. We're only using a few integer variables like total sum, minimum absolute value, and the negative count. But these are all integer variables. These are not any extra data structures that use auxiliary memory. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.